minimum spanning tree, but now we're going to be talking about like different sorts of greedy algorithms. Okay, and kind of the high-level recipe for greedy algorithms is like, you have a bunch of choices. It's kind of like dynamic programming, but a little bit simpler. It's just like you just make a choice, maybe the best choice, and you kind of never look back and just keep going. Okay, and we'll see some examples. And it's kind of like one of the one of the tools that you should have, like every time you see a new algorithms problem, not just in the class, but like out in the world, like you need to you solve something, you need to do it fast, and like usually greedy algorithms are pretty good, and then, I mean they might not be the best in many cases, but like they'll be good enough in many cases. Okay. So let's get started. We'll just see a bunch of different examples of greedy algorithms. And they'll all have like a common structure, as you'll see. Okay. So so we'll see 3 interesting examples of greedy algorithms. Okay. So first is a non-example, like something that won't work if we use a greedy algorithm. Okay, and it's the knapsack problem, and we kind of saw this when we studied the dynamic programming, right? So the knapsack problem is the following: I have a bag which it can hold a certain number of weight, and there's a bunch of items, let's say an unbounded number of each type, and each item has a weight and a value, and the goal is, right, to put as many items in your bag so that your bag doesn't explode, but you want to take as much value as possible, right? And you can solve this with the dynamic programming. Okay, like the subproblem is, right, what do you do at weight at a certain weight w. There's some choices, right? You take one possible items, that gets you to a previous subproblem based on the weight. Okay, so you can solve this using dynamic programming. But right, so if I have a bag that can only hold 10 things, then it turns out this is the best. Okay, you get item 42. But now let's think of a greedy algorithm, right? A greedy algorithm will say, okay, right, what is the best item to take? Well, it might be the one that maximizes value per weight. Okay, it's like, what is the best value that I can get per per pound of weight. Okay, and if you do that, then it turns out, well, you just take this item, tacos, and then like, okay, then right, then you don't get the optimal. Okay, so knapsack is not an example, but actually you can show that if you use greedy, then you get a factor of 2 approximation, meaning you're not going to be off by more than 50% or something like that. Okay. So that's a non-example of a greedy algorithm. Like this is a case where a greedy algorithm does not work. But we'll see some other examples. Okay, very well. But yeah, okay, so knapsack. So okay, so now let's just go to the first example. Okay, and this is a very classic example. Okay, so the problem is as follows, right? I have time, right? Like from 9 a.m. to 9 p.m. and there's a bunch of activities that I can do, right? So a certain activity takes a certain block of time, right? Like maybe between 12 to 1 you have to have lunch, and maybe between like 5 to 6 you have swimming lessons or whatever. Okay. So you have a bunch of activities to choose from, and now the problem is as follows. Okay, I want to pick the most number of activities that I can do that don't overlap in time. Okay, so it's like, I can't go to my whatever basket weaving class and have lunch because they happen at the same time. Okay, so the problem is, right, I want to pick the most number of non-intersecting activities. Okay, does the problem make sense? Okay, and then this is like a classic example where a greedy algorithm does work and is the optimal algorithm. Okay, but right, it's not so clear what a greedy algorithm means here. Like there's a few choices, right? Like when we go back to the knapsack example, right, if you were to use a greedy algorithm, then the natural choice is to use this like value per weight, right? Here there's a few choices, and we'll see them. Okay, right, like I said, you can only do one activity at a time, and your goal is to maximize the number of activities that you can do so that they don't intersect in time. Okay, so that's the problem. All right, so to be more formal, right, I have a bunch of the activities. They both have a start time and a finish time. And like I said, the goal is to pick the maximum number of activities that don't intersect, okay, between the start and finish time. Okay. So in general, with greedy algorithms, you kind of do things one at a time. So it's like, okay, you consider one choice at a time, So here it's natural to say, okay, in which order do I add activities to my potential schedule, right? So one idea is like, well, you just say, okay, maybe I pick the shortest activities first, right? I add that to my schedule, and then I try to fit in other activities and so on, okay? So that's one example. So we'll see a few different ways to sort of think about greedy algorithms, and some of them won't work, and some will work, okay? But in general, like greedy algorithms have a template, which is like you consider all the choices in some natural order, and then you greedily make the choice as long as it's compatible with the choices that you've already made. Okay, so here, right, what we can do is just like consider the activities in some order, and I keep adding them as long as they don't violate, the fact that I can't have two activities at the same time. Okay. So let's just see an example. Okay, so here's a very natural greedy strategy, okay, which is I order the activities by how long they last, starting from the the activity that lasts the fewest amount of time to the longest activity. Okay, so what that means is, right, I order the jobs or activities in order of finish time minus start time, right, which is how long it lasts. Does this work? Will this give me the optimal schedule? Right, my goal is to do as many activities as possible during the day. Okay, that's my goal. Any intuition, idea, and like I mean, obviously, if you go to the next slide on Canvas, you'll see it. But like just some intuition, yeah.
I guess no, because let's say that you have like two jobs that are long, or like two jobs that are longer, and then the middle, the shorter one, that's just slight overlap. You'll pick the middle one, but the longer pick, the more jobs to pick the two outer ones.
Right, exactly, right. So here's an example, right? Say you have 3 activities, right, and the kind of the fastest activity, the one that lasts the least amount of time, intersects with both of them, right? So this is not a good greedy solution. Okay, it won't give you the optimal answer. Okay. So let's see another. Right. So the problem with this was like this activity was conflicting with like lots of different activities. So we can say, okay, what about if we order the activities in terms of like the fewest conflicts, okay? So we order the activities in terms of the number of other activities they intersect with. Can this work? Okay, yeah, this one's a little bit harder to think about, but yeah, you can see like every okay, so the optimal one is to kind of take these 4, right? Then you get to do 4 things. But you see that like every activity is intersecting with a lot of different activities, except this one, right? It's only intersecting with 2. So then like this greedy strategy would take this one first, but then you can't do more than 3 things, okay? So this is also not a good thing. And you might say like, okay, I'm going through a few examples, like how do I know which one to try? Well, that's the fun of algorithm design, right? You kind of have to come up with a strategy, and maybe some of them work, maybe some of them don't. Okay, what about this one, earliest start time? So I'm not even looking at the length of the job or the activities or anything else. I'm just saying which ones finish first. Okay, I don't care about the start time. Which ones finish first? In terms, okay, oops. All right, well, this one also does not work, and you kind of see, right? Like if right, or sorry, which one starts first? Sorry, I messed up. Which one starts first? You can see like this one starts first, but it just lasts a really long time, so this also doesn't work. Okay, now one that actually works, I guess, right? Based on what I was saying, is I'm gonna be looking at the activities in order of which ones finish first. Okay. So this one will actually end up being a good greedy algorithm. It will give you the optimal solution. Okay. So yeah, this will be the right way to order the jobs. Okay. In order of finishing times. Okay, so what is the greedy algorithm, right? I like order all the activities in terms of their finishing times, okay? And then I say, okay, I'm just gonna repeatedly pick the activity that doesn't intersect with, right? I mean, first I have to remove everything that intersects with my existing schedule, but the next activity I pick is the one that finishes first among the ones that are valid, okay? So let's just see that in, right, so let's see a quick example of that. So in the beginning, okay, this activity finishes first, so I pick that, and then I cannot pick the first one, right, because that intersects. So then I don't consider that, but then the next activity that finishes first is this one, right? And then I pick this one. Then I can't pick the next one because that one intersects with the activities that I already have. Then I pick this one, can't pick this one, and so on. Okay. Does that make sense? How I pick these four activities? Okay. All right, and I mean, I haven't proved that it's optimal. We'll see that, but at least I don't have to convince you it's fast, right? All I do is sort things, so it's pretty fast algorithm. And usually, greedy algorithms, because they're never right. I never looked back, right? I didn't say, okay, can I add a new activity and remove some things in the past, right? That would have made a more complicated algorithm. So in general, greedy algorithms are also very fast because they're just making one choice and not even caring, if I could substitute something in the past. I just pick a choice and just continue with my life, okay? Oops, okay, so now, yeah, so let's again look at the template, right? Let's right, what made it a greedy algorithm, right? It's, again, right, I'm saying the same thing over and over again, but it's I have a partial schedule, and I want to extend it by 1. And I extend it as long as it doesn't conflict with things that already had happened, okay? And then how do I extend it? Well, I pick some rule to extend, okay? And this is exactly what we did for minimum spanning tree, right? We had a, we had a tree that would cover, that connected some number of nodes, and then, right, we extended the tree by 1 edge at a time, as long as it didn't conflict with anything, right? So previously it was, right, as long as it didn't make a loop with anything that we had. And then, right, the greedy choice was just, well, I picked the one that's the smallest edge crossing the cut. And that's kind of what's going on here. Right, in the minimum spanning tree, right, I never went back and fixed the tree, right? I just said, whatever tree I had, I'm going to keep it. I'm just going to extend it 1 edge at a time. Okay? And, right, we're going to have some structure, right, that allows this to be the optimal algorithm, right? In general, you can imagine settings where if I don't look back, right, if I never fix my mistakes, there's no way I can get to the best solution. But we'll see, there's going to be a special property that will exploit, which kind of lends itself to, to this type of analysis, okay? Yeah. So in general, you might ask, okay, we've seen kind of 2 examples, right? Minimum spanning tree and this example, which I haven't proved yet, of greedy algorithms. And you might say, okay, when do I know when to use a greedy algorithm? And in general, these algorithms are useful when your problem has a special property, okay? It's hard to quantify what that property is, so let me just kind of give you a high-level idea. It's essentially, if it's always possible to extend a partial solution by 1 and maintain the fact that it's part of some optimal solution, okay? So that's kind of what happened for minimum spanning tree, right? If I have a partial tree that's part of some minimum spanning tree, there's always a way to extend it by 1 so that it continues to be part of the some optimal minimum spanning tree, okay? And that's essentially when greedy algorithms are good, which are you can extend your solution by 1 and still maintain the fact that you're a subset of the optimal solution or some optimal solution, okay? So try whenever you see this anywhere else, most likely in the test or homework, right? Try to do this kind of try to have this in the back of your head, okay? All right. So let's prove why this works, okay? Why does being greedy in this particular way give you the globally optimal schedule, right? It gives you the best way to pick activity, the most number of activities without intersecting. And then my previous discussion kind of hints at what we're trying to do, right? We're trying to say if I have a partial schedule, I can extend it by 1, okay? So that's essentially what we're going to do. All right, so yeah, so let's say in the beginning, right, I picked this activity due, and it's part of some optimal schedule, okay? There's some optimal schedule that contains this activity, right? So initially, right, let's just assume, right, Let's just assume that, okay? And now I want to show that the next choice I make will maintain the fact that it's part of some optimal schedule, okay? Yeah, so so let's just say, this one we picked is, in the beginning it's part of this optimal schedule, okay? So we want to show that whenever we make the next choice, we don't rule out being optimal. All right, so okay, let's prove this formally, okay? So like I said, in the beginning I picked this choice, and then I'm going to use, I'm going to assume that so far whatever I have is optimal, okay? Or it's part of some optimal schedule. I want to show that the next, whatever the next choice that I make, I can extend it by one, okay? So I'm saying the same words, but I think the picture will be more clear, okay? So now, now this is the important slide, okay? So, I've already made this choice. This is part of some optimal schedule. And let's say the optimal schedule from now on looks like this, okay? You pick this one, and this one. But greedy will end up picking this one, right? Because we're picking by the earliest finish time, right? So that's a problem, right? So far, so far up to this point, we're on track with some optimal schedule. But then we make a choice, maybe that differs from the optimal schedule that we're following. And now, now we need some argument to show that, well, that wasn't so bad, okay? Any idea, what we should do? Okay, so just to say where we are, okay? So from any time before, let's say we picked the optimal schedule, okay? And this is our choice, right? The first choice was optimal, let's say. It's part of some optimal schedule, this orange one, okay? But the next choice that we make is not part of this, right? We end up picking this one. Why is that not too bad? So what did we do with minimum spanning tree, right? We said, okay, whatever edge we pick, it may not be part of the minimum spanning tree. But we can find a way to add that edge and remove something else. Okay, so essentially that's what we're going to show. Yeah, so what happens if this is not part of the optimal schedule? Well, then it must intersect with something in the optimal schedule, right? If it doesn't, then the optimal schedule would have had that, right? That's for free. And what we do is we just swap them, okay? We swap them. Why is that okay? Well, this job that we picked, or this activity that we picked, ends the first, right? Ends earliest. So if we swap these two, it's not gonna, it's not gonna intersect with any other activities that the optimal schedule has picked, okay? And the reason is, right, the optimal schedule ended up picking this thing, and the thing that we picked only ends even faster, right? So it's not gonna intersect with anything else that the optimal schedule has. Does that make sense? Why it's okay to swap, right? Like I'm saying, right, let's say, this is the orange part is the optimal schedule. For some reason, I've already picked this one. That's my partial schedule. And then the next choice I make is this, but then optimal ends up making this choice, right? And that seems bad because we're no longer tracking the optimal schedule, right? But all I'm saying is, in that case, we can swap. Why is that okay? Why would that schedule still be optimal? Well, it'll only be bad, right, if we're reducing the number of activities, right? And the claim is that we're not going to be reducing the number of activities because the thing that I ended up picking is not intersecting with anything that the optimal has. Okay, so this orange thing on top is still is another valid optimal schedule, and we're tracking that now instead. Yeah.
What if we need the optimal solution to be considering how long we're spending?
Yeah. So right. So just by definition of this problem that we're considering is just we're fitting the number of activities. Okay, that's the problem. But yeah, if you change the requirement to say something to do with time or cost, then it'll be a totally different problem, and then we'd have to do something else. Yeah. So for this problem, right, we're purely interested in fitting the most number of activities, right? We don't care how long they last. We just want to do the most number of activities. And then, yeah, just to kind of summarize, right? It's okay that I didn't make the optimal choice, because if I just swap, then I'm still okay, because I'm not going to be intersecting with any other future activities that the optimal schedule is doing. Okay, and the reason is because I picked the one that ends the fastest, or ends the earliest in time. It's of course going to end even. It's not going to go past the optimal one, right? And that means since these don't intersect, this one and this one will also not intersect. Okay. So that's all I'm saying. Yeah, so what am I saying, right? It's like if I had a partial schedule, I can extend by 1, and it will still be tracking some optimal schedule. Okay? And that's essentially what we had with minimum spanning tree, right? Like I have a partial tree that's tracking some optimal minimum spanning tree. I add one edge that will still be tracking some optimal minimum spanning tree. Okay? Does this make sense? Okay. So then like I'm going to go forward a bit, and then I'm going to go back. But essentially, right, what do we do, right? We prove this step of the induction, right? Like initially, right, if you want to write this formula, right, it's like, well, what I'm going to do is show that at every step, I'm going to be tracking some optimal solution. In the beginning, right, it's empty. So that's a subset of some optimal schedule. And then now I say, okay, what is the inductive step? We're going to say, if I have a partially optimal schedule, I can extend it by 1. That's essentially what we just showed. Okay, and then then the whole thing will follow by induction. That's why induction is so powerful. It's like we just have to show that one step, and then if we show that one step, right, sort of all the dominoes fall. Okay. So now let's go back. Okay. So what we just showed is that if I have a partial schedule, then I can extend by 1, and it will continue to be a subset of some optimal schedule. Okay. Okay. Any comments? Okay. All right. So now let's move on. So like I said, right. So kind of why would this algorithm be optimal? Well, it's like we never rule out an optimal solution, right? We're always tracking an optimal solution. And at the end, right, we have some solution. We can't extend anymore. So that means we have some optimal solution. Okay. It's like at every step, we're tracking some optimal solution. We never deviate, right? Like partially, I'm partially tracking an optimal solution, and then the next choice I make may not be exactly the same choice, but it's actually going to correspond to some other optimal schedule by doing this swap. Okay. All right. Comments? Okay. Questions? Yeah, and then like if you want to be super detailed, right? Like, or like if you want to prove things I mean, it's like pretty obvious, right? Like why this is true. Like I keep tracking the optimal, but if you want to write things formally, right, you have to use this. You have to have a base case, induction hypothesis, and then proof by induction, right? Okay. But yeah, I mean, if like in the exam you kind of just show that okay, I can swap, and the swap has this greedy property. That's all we want, right? Because this is kind of like obvious how you'd fill in the induction. Okay. All right. Okay. So now we're finished with this example. Anything before we see the next example? Yeah. So just to go back to this template, right? Like basically the property that we used is that I can extend a partial solution that I have by 1. Okay, so this is exactly the same property we use in minimum spanning tree, and usually in greedy algorithms, like the thing that's underlying it, like underlying why they're correct, is basically this reasoning. Okay, somehow you need to show that I can extend a partially optimal thing by 1. Okay. All right. Yeah, like I said, how you prove this is by induction. We don't need that, right? So now let's like dive into this a little bit, okay? So like I said, right, we need to show this kind of important step where if we have a partial thing, we can extend by 1, And most of the time, that's where like the hard part is, right? Like, how can I argue that whatever the next thing I added, it's still valid or still like tracking some optimal solution? And that's going to involve a different argument for a different problem, right? So for minimum spanning tree, the argument was like you add the edge that should have been added, then you get a loop, then you can remove something. Here, the argument was, well, you know, if I added an activity that the optimal schedule didn't have, then I can swap, right? Like instead of the optimal having that activity, I can swap it with my activity, and then it will still remain optimal. Okay. So in general, like kind of you have to do this like this argument where you swap. Okay. So it's like same with minimum spanning tree, and it's the same here. If we're not tracking the optimal solution anymore, then we can kind of force ourselves to track it by saying, okay, whatever choice the optimal was made, that's different from our choice. Well, we just let the optimal make our choice, and nothing changes. Okay, it still remains optimal. Okay, so what that proves is is like, oh, we've tracked it so far, then we track it for one more step, and then if we keep tracking it for all steps, then we have the optimal at the end. Okay, so yeah, it's a very like intuitive idea. Like like if at every step you're not making a mistake, then you'll never make a mistake. Right? All right. Yeah, and like this is not the only way to prove that greedy algorithms work, but for most of the things we'll see in this class, like this is pretty much it. Okay, you just do some swapping argument to say that okay, the greedy choice that I made is not too bad, or like it won't hurt me if I make that choice. Okay. All right. Okay. So, right. So, and you might say, okay, this looks a bit similar to dynamic programming. And in some sense, it is. Actually, greedy algorithms can always be analyzed using dynamic programming, or like this swapping kind of thing can always be analyzed. And you might say, okay, what is the subproblem? Well, the subproblem is going to be the number of activities you do after this time. Okay, that's the subproblem. So kind of like we covered 3 techniques, right? Divide and conquer, dynamic programming, and now greedy. And they all kind of have this subproblem property where, like, to solve a problem, I'm actually solving a smaller instance of the same problem. Same with this like greedy scheduling, right? It's like, well, the best schedule, after some time is, well, I just run the same algorithm on the subset, right? So essentially, if I like draw a tree, then they end up looking like this, okay? Divide and conquer, right? I break it into subproblems and I go down. Dynamic programming, right? The subproblems may call on each other in more complicated ways, right? Like it's not true that it's not true that as in divide and conquer, right? Kind of the subproblem here is kind of originates from one subproblem, right? In dynamic programming, right, we need to remember answers so that we may call on like arbitrary answers throughout time. But greedy algorithms have a much simpler structure, which is essentially most of the time like you're just making one choice and you're never looking back. So in some senses, like you just chop off one thing at a time. Okay, so they're actually very easy to think about in this way. So right, with the optimal scheduling, right, or the thing that I just talked about, I just go left to right, right? I never go back. I never look at any other subproblems. Only thing I care about is just going left to right. Okay. Yeah. So it turns out that even this activity scheduling problem, you can solve this using dynamic programming, and maybe it's like a worthwhile exercise to think like what is a dynamic programming solution for this. But right in this case, the greedy algorithm is just much easier to like reason about. Okay. Yeah. Yeah, and the one thing is is like we never have to do this combined step, right? We're just saying, well, I just do one thing, and then like I just take I just make one choice, and then it's not like I have many subproblems I'm looking at. I'm only looking at one subproblem, which is the rest of the remaining activities. Okay. So that's all this diagram is saying is like somehow one problem only depends on one subproblem, right? I just made one choice, right? A greedy choice, and I keep going. I never look back. All right. So now let's see 2 more interesting examples. Okay, so this is another scheduling problem, slightly more complicated. Okay, in general, like you'll notice, like most scheduling problems have a greedy algorithm. Okay, and they like, so for instance, right, whenever whenever like beginning of the semester, right, there's thousands of students at Madison, and they all have like classes and conflicts. Actually, somebody is running a scheduling algorithm. Probably it's outsourced to like some company that's doing it. I mean, I have no idea, but essentially, at some point, they're going to run some code that uses like pretty much related scheduling algorithms. Okay. All right. So, like now, okay, now I have a bunch of things I need to do, but now I care about how long things take. Okay. So now it's a slightly different problem. Okay. So previously, I only cared about doing as many things as possible, but now I have a penalty for not doing some activities. Okay. So now, what is the problem? The problem is a little bit different now. Okay. I have n tasks. And each task takes some number of time, and every time, and if I don't do something for a while, I have to pay some amount of money, let's say, or like some penalty. Okay. So for every hour that passes until some task is done, I pay cost ci. Okay. So for instance, let's say I have some class, or I can do some homework, or go to sleep. The answer is obvious, right? You do the homework. I'm kidding. Maybe you sleep. And let's say, right, homework takes 10 hours, sleep is 8 hours, and for every hour until the homework is done, you have to pay 2, okay? And for every hour until you've slept 8 hours, you have to pay 3, okay? So then there's, if I just have 2 activities, then there's 2 things, right? First, I do the homework, then I sleep. Well, right. So how much does that take? Well, the homework takes 10 hours to finish, and then it's 2 hours. 2 cost every time until I don't, right? So it's 10 times 2, and then I sleep, right? Well, I haven't slept for the first 10 hours, so I have to pay that penalty, right? 18 times 3, okay? And then the other thing is, well, if I sleep and then I do homework, then it's the same calculation but flipped, right? But then I only pay 60, okay? So this is a problem, okay? I have a bunch of tasks to do, and every hour that a certain task is not done, I have to pay a penalty, okay? And the problem is, how do I, so I have to do all the jobs, right? Previously, right, I didn't have to do all the activities. I was trying to find a subset of activities to do. Here, I have to finish all the tasks, but in which order do I finish the task is up to you, okay? That's the math part. Like, we need to figure out what is the optimal way to do the task to minimize the costs that we pay, okay? Any questions about how these like numbers came to be? And like you can imagine this, there's many problems that can fit this mold, okay? We just made something up, but you can imagine many things can fit this mold, okay? Okay. So right, this problem also has this thing called this optimal substructure. So what does that mean? That means is like, okay, let's say the optimal optimal order in which to do the jobs looks like this. Okay, you do A and then B and C and D. Okay. What this means is if I pretend task A or job A doesn't exist, then B, C, D is the optimal order for B, C, and D. Okay. Why is that? Right? Let's say A, B, C, D is the optimal order for these 4. Then my claim is that if I look at any like subset of time, right, afterwards, then this subset is also the optimal order for these 3 jobs. Right? This was the property that we needed for this interval scheduling, right, that we saw before, right? After some time, right, anyways, yeah. Why is a subset of the, a subset of the of these jobs also an optimal schedule? Yeah.
I think it's because for the whole thing to be optimal, job A must be like the most costly one. So, and then they must go in descending order of cost every job.
Yeah. So I'm asking a slightly different thing, which is I'm saying it doesn't even matter for this problem. I'm saying in general, like for some like scheduling problem where I have some other considerations, I have some schedule, right, which I do job A first, B, C, and D. Then I'm saying, okay, let's pretend job A never existed, and I only had 3 jobs, B, C, and D. Then I would also choose to do them in this order. And the reason for that is, well, like if not, you could rearrange things, right? So I think that's kind of what you were getting at, which is like, right, any sub schedule of an optimal schedule is also optimal, because otherwise you would just rearrange the subschedule. Okay. So this is I'm not saying anything deep. I'm just saying like if this was not optimal, you could rearrange. Okay. And this kind of like lends itself to how you would actually solve this problem, which is, well, then if I can somehow figure out what the first thing to do is, right, then like I've reduced to a case where like it's a smaller instance of the same problem, right? And that's exactly what we need, right? Like first I figure out what the best job is. If I can do that, then I've kind of shrunk the problem size, right? I went from n possible jobs to n minus 1. Then it's the same problem, right, on a smaller input, and I call it again and again and again, right? Right, so that's what I'm saying. Okay, so now let's get into more details about what it means to what it means for one job to come before another job, right? Like why would we ever? Let's just say I have only 2 jobs now. Like I said, right? Let's say the first one takes some number of hours. The second one takes y hours, x and y. The first one costs z units until it's done. The second one costs some other amount of time or some other amount of cost. And let's just say I only have 2, right? How do I know which one to do first? Okay. Well, it's just like I just do some math, right? So, wait, what is the cost of doing A and then B? Well, if I do A, right, it's x times z, right, until it's done. But then I haven't done B for x hours, right? So then when I do B, I have to do x plus y times w, okay? Because like the first amount of time that I was doing A, I haven't touched B at all, okay? And then the next choice is, well, I can do B and then A, and then I get some other expression. So why would I, how do I know which one to pick? Well, then I just set them, I compare them to each other, right? I say, okay, when is, the first choice, AB, better than BA? Well, then I just write down this equation, right, move some things around, and then I get to this quantity, okay, this ratio. What is this? Well, it turns out, right, if I just have 2 jobs, then I want to do the one that maximizes the cost over the time, okay? Right, so I didn't do anything, right? I just said, okay, if I only have 2 jobs, right, I can do A and then B or B and then A. This will lead me to like different amount of cost, right? This in one case, this in one case. And then I say, okay, why would I do one versus the other? Well, I have to compare these 2 expressions, right? And then I subtract common things. I make it into a nice expression and say, oh, look what popped out, right? Something really nice popped out, which is, well, this is the cost per time, right? Cost per time. So I only do, so it's like saying if I only have 2 jobs, right? They may be varying in lengths and varying in costs, but the thing I care about is the cost over time, okay? So if I only have to, okay, so if I know this, right, what is a natural greedy idea to do, to solve the whole problem? If I know that for 2 jobs, right, I have to arrange them according to this cost per time ratio. How do I do the whole thing? Like, what is the natural extension of this? Oh, yeah. Yeah, so it's the opposite. You pick the one with the most. But yeah, it's like, right, so if I have n jobs, I just sort them in this order of cost per time, okay, from largest to smallest. And then I just follow the jobs in that order, okay? And that's going to be the best, right? That's going to minimize our notion of overall cost, which was you have to pay some time, you have to pay some cost per unit of time that the jobs are not being done, okay? So right, so what happened here, right? I just said, okay, if I just imagine I have like only two things, how do I arrange them? And that kind of hints at how to arrange everything else, okay? All right, so like I said, what you're going to do is you're going to greedily keep picking the jobs with the biggest cost per time ratio, okay? All right, and now let's prove that this will give you the optimal way to do all the jobs, okay? And right, this is like, if I just told you this problem, this is not an easy problem, because there's so many different ways. There's like n factorial ways to go through all the jobs, right? And I'm caring about this like very particular thing, which is, you know, total cost I paid times like the delay factor and whatever. But it turns out it has a really nice answer, right? Which is I just sort the jobs in terms of, you know, cost per time, and that's the order in which I do them. Okay. So now let's prove why this works. And the proof is essentially the same, okay? Right? Let's just say, right, you know, this is the ordering of the jobs, right, in terms of cost per time, okay? This is the ordering that I want to follow. And let's say, you know, somehow the first job agrees with the optimal ordering, okay? Right? There is an optimal ordering, which I don't know. And let's say the first job in this ordering works, okay? Now I want to say, if the first one works, then the next one also works, okay? That's the induction, right? I mean, ideally, I would start with no jobs done, then I can show the first one. But, you know, I'm just kind of showing you what the induction hypothesis step will look like. Okay, so, but at a high level, all I'm doing is saying, if I have, like, you know, partially, right, partially I know this is the optimal ordering so far, how do I know the next one I add is also part of the optimal ordering, okay? So why would it not be? Well, oh, sorry, this is it. Yeah, sorry, this is the optimal ordering, let's say. And the one I'm following, let's say, matches the first one. And then somehow I ended up picking something in the middle, okay? Sorry, I just flipped it. Instead of showing our, I showed the optimal, okay? So again, just to recap, this is the optimal ordering. I picked the first one, let's say. I followed the optimal ordering so far. But then, for some reason, the greedy algorithm ends up picking something randomly in the middle. Okay? Any idea then what we can do to show that, hey, actually, it's okay for it's okay for optimal to also do job B next, right? So, yeah. So, like, right, what did we just say, right? We said if I have two jobs, right, then the best thing to do is like follow in this ordering, right? So if greedy ends up picking something, right, that's really like very different from the optimal, well then I can always swap, okay? Yeah, let's see a diagram, okay? Or let me not make it too complicated. So all I'm saying is, okay, this is the ordering the optimal schedule is following. I do job E, C, A, B, and D. But somehow, let's say I do E and B. Well, then I can say, well, I can actually make optimal not worse. Maybe I'll improve it, maybe I won't. But it won't be worse, right, if I swap B and A. Why is that? Well, B and A have not been, you know, the calculation I showed you, right, is, well, greedy picks the one with the best ratio, right, cost per time. And if I have two jobs, then the best way to order them is by cost per time, right? So I know that B is better than A in that ordering. So then I swap. And then I swap B and C. And then I get to another schedule, right, that's as good as the optimal schedule, right? Because every swap that I make does not hurt the optimal schedule, right? That's essentially the math that we just did, right? It's always better to follow in terms of cost per time, okay, if I just have two jobs. So all I'm saying is, if the next choice that greedy makes is somewhere down the line, well, I can keep like making swaps, right, and get it so that B is next to E. Okay, then you get E and B. And that has not hurted optimal, right? The optimal solution stays the same, or like maybe even improves. You know, it doesn't get worse because I did this swapping. Because I only, you know, why was it valid to swap A and B, right? Well, B has a better cost per time ratio. Yeah, sorry, you look confused there.
Yeah, I mean, I just feel like, so you have like this order right now, and now you're swap, like this is your
No. So this is like an experiment I'm doing in my head. So I'm saying, imagine what the optimal ordering looks like. Okay. So I'm saying this is the optimal.
That's your imagination.
That's imagine, right? That's my imagining of the optimal. And I'm saying, okay, I want to keep track of the optimal, right? Like I've kept track of the first job. Like the first job that I do is matches with the optimal. Great. I'm happy so far. But let's say somehow I ended up picking, the next thing to do is like down the line, right? Optimal doesn't do it until a while. Well, I'm saying, well, I might as well make optimal do it right after E by swapping. And why is that, right? I'm saying if I swap B and A, optimal actually gets even better. Why is that? Because B has a better cost per time ratio than A.
You're like trying to think of the next best one with the best ratio.
Exactly.
Not your imagination, you're trying to like swap it.
Yeah, exactly. Yeah, exactly. Yeah, it's like it doesn't, yeah, exactly, right? Like I'm following this greedy algorithm, which is picking by ratio. I don't know what optimal is doing, right? It could be doing, it's like something in the sky, right? It's the best thing that can happen. It may be following a different ordering. But I'm saying I can force it to match the ordering that I'm doing by swapping. And I just showed you, right, if I swap things by this cost per time ratio, it doesn't hurt you. So I can force optimal to match me one more time. Okay. Yeah, so another way to say is like if the optimal doesn't look like what I want it to do, I can like sort of manipulate it or change it to make it look like what I want without hurting it. Okay? Right, so essentially that's what it's saying, right? It's saying, okay, well, yeah, so far optimal does not look like me, right? I do E and B, optimal does E, C, A, and B. Well, then I can consider this thought experiment, right? What if optimal had instead done BA instead of AB, right? That would have never hurt optimum, the optimal solution. Because these things, right, have, B has a better cost per time ratio, right? And I just showed you, right, for two things, it's always better to have the cost per time that maximizes cost per time in front. Well, then I just repeat this argument, right? If there's something in between, then I just, well, by definition of greedy, right, B has a better cost per time ratio, so then I can swap. Okay, so kind of similar to minimum spanning tree, right? I'm saying, right, I'm building this solution one thing at a time. At some point, I might deviate from the optimal. But actually, I can force optimal to look like me, right? In the minimum spanning tree case, right, if the edge that I picked was not in the optimal, I could add it to the optimal and remove some other edge. That's essentially what we did, right? That was like the loop thing. Here, the same thing, right? If the optimal is not following things in the same order as I like, I can force it to follow in the same order. And why does that not hurt the optimal? Well, I just proved, right, between any two things, I have to, the one that minimizes or maximizes, cost per time is better to have in front, right? That was that inequality calculation we did. Well, then I say, okay, imagine instead optimal did CBA instead of CAB. It only got better. Then I imagine one more step. Oh, imagine if it did BCA instead of CBA. Well, it only got better because I swapped things that were incorrectly sorted, right? Okay. So essentially this has the same structure as the previous thing, right? Which is if optimal does not look like what I want it to look like, I swap it. But then the reason is like, why does the swapping thing preserve the fact that it's optimal? That's the key step, right? Of course, I can swap things, but then it got a lot worse, right? Then okay, then what did I do? I didn't make any progress. But really, I'm using the fact that, right, it's like very particular to this problem, right? I'm using the fact that I can always swap things that have, or like if I have two things, the thing that has a better, cost per time ratio can always be assumed to be in the front. That can never hurt me. That's essentially the property that I'm using, okay? All right, yeah, and like I said, we just did this inductive step, right? I tracked optimal up to E, and now I can track it up to the next job. And then by induction, I've tracked it for all the jobs, okay? Any questions? Yeah.
So like, what's making that first one optimal at all if like we're improving it?
Yeah. So imagine like this, right? Imagine I haven't picked anything so far, right? It's still tracking optimal, right? I'm just saying before time has even started, right? I haven't done anything, so it's still part of optimal. So the base case is like trivially true. Now I say, okay, why is the first choice okay? Let's say the first job that I do, that greedy does, is like job number 10 in the optimal schedule, okay? Well, then I do this thought experiment, which is, okay, it's job number 10, but imagine Optimal had done it job number 9 instead. I swapped 9 and 10 in the Optimal scheduling. Optimal didn't get worse, right? Because these 2 jobs that I swapped, 9 and 10, well, this one that I needed had a better cost per time ratio, right? And I just showed you, if I just have 2 things, the one with the better cost per time should be in front. And then I keep doing the swap, okay? So that's why the first thing is also good. Okay. Yeah. Yeah.
I have like a similar question.
Yeah.
Like I get why you're switching it because
Yeah.
you're trying to follow the greedy
Right.
procedure, but I don't understand like how that like why the optimal is even better if it's not at all.
Right, you can imagine there could be different, like imagine the minimum spanning tree, right? There could be different solutions that are the same value, right?
Okay.
Right? And like, yeah, there could be different things that are the same value. And like, of course, at the end, right, I have shown that like there's one optimal that is exactly the greedy solution. But I don't know that before the fact, right, a priori. I don't know that a priori. I want to show that. So just imagine, that's why we say, okay, assume that optimal is, you know, something different. Then I can force it to look like me, and it won't have gotten worse in quality. That's essentially the argument I'm doing. Right, just to repeat, right, exactly, like, you know, there could be many optimal solutions, right? I don't know. They could look very different, right? This is a very weird, this is like too many options, right? There could be many things that lead to the same value. So then I just pick one of them to follow, okay, one of them to track. In the beginning, right, I haven't done anything. That's fine. And then I say, well, what is the first job that I do? It maximizes the cost per time ratio. And the optimal that I picked to track, well, it doesn't have the first job the same. That's bad. Well, then I take the one that I did and I move it all the way to the front. And I say, oh, actually, the thing that I was following didn't get worse, right? Because I only did, you know, why did I bring it all the way to the front? Well, I swapped 2 at a time, and every swap did not hurt it, right? That was this like, you know, kind of algebra that we did, right? If I have 2 things, it's better to put the one that is has a larger cost per time, right? So then I can use that to swap all the way to the front as I need it, okay? Yeah, so you know, with these proofs, right, you're always like imagining something in your head, like what does the optimal look like? And then I'm saying, well, I can actually match it. Okay. But I mean, if this was like confusing, at least like know that like, you know, at every step it makes sense to do this cost per time ratio, because right, if I have 2 things, at least right, this math makes sense, right, which is it's better to do the the one with a larger cost per time, okay? So, all right, and you know, this is not too slow, right? I just have to sort, so it's n log n, okay? Any other comments, questions? Yeah, so let's do this one first.
So when you usually kind of with the greedy, are you always going to prove it inductively and use the greedy in the inductive step?
Yeah, so you know, even in tests, like you don't have to write out the full induction, right? What is the main step? The main step is showing that this swap property works, right? Which is, so that's essentially what you have to show. Okay. Yeah. Or like even in the first example, right? Right, there was also a swapping going on, right? Like I didn't try, you know, the activity I picked was not the activity that optimal picked, and then I could swap it and like not hurt the optimal solution. And then now it looks even more like me, and I keep going, right? So like that's like the key idea, right? Like, you know, I mean, you can write page, you know, people can write pages and pages of induction, but if it doesn't have that key idea, then it's kind of useless, right? Yeah.
So with all this algorithm aside, you want to kind of have, do you want to do like the most expensive cost ratio first?
Yeah.
And go all the way to like least
Yeah.
cost ratio? But
Yeah.
that's essentially just turn like a ordering problem into a sort problem, then this becomes first sort to say that you have running time is long end.
Yeah, so the running time here is kind of obvious, right? You're just sorting. The hard part is proving why it works, right? Or like that's the interesting part. And essentially that there's only one idea, right? Which is swapping 2 things that, you know, that have the incorrect, you know, like if I have 2 things, the one I want to put in the front is the one with the better ratio. Right. So that was like one calculation that we had to check, right? That was particular to this problem. If I changed the problem and it was like, well, I didn't care about time, it's just like every job had a money associated with it, I just wanted to maximize the amount of money, then it'll be the first, you know, it'll be kind of like the first problem, right? So, you know, it's really about like, you know, if I change some things, the problem just becomes very different. But just for this particular thing, like the main thing to check was like, how do I know which things to swap? And it was like, oh, okay, it was the ratio. So in like, in an exam, like, it'll be kind of similar, like, well, how do I know which order to do things? Well, like, I need to come up with a greedy strategy, and that has to be motivated by something, right? It has to, like, you can't just be ordering randomly. So you need some reasoning about how you're getting the ordering, okay? All right. Any other questions? So I think that there are some other questions. Yeah, you good? Yeah.
We got like the ratio at first page, so like is that possible? Like we just like sorted it by the ratio, so it's like and we could like this is like it's better than the original like optional first.
Yeah. So the algorithm has no idea that we did this analysis, right? All the algorithm is seeing is sort and return that ordering, right? It's just the analysis is like we're doing this thought experiment where imagining the optimal. If it does not look like how we did it, then I can swap things to make it look like how I did it, and it would not hurt the optimal. That's essentially the argument, okay? Yeah. But yeah, the algorithm has no idea we're doing this swapping, right? This is all like hypothetical, in our head kind of thing, yeah. Okay, so now let's see one more example. So we have 15 minutes. Okay, so this one is like more of an advanced example that we won't see in the exam or homework, but it's pretty cool, okay? It's an example of a greedy algorithm that is used all the time, okay? So it's called Huffman coding. It's like, how do I encode, like language into bits? So if you've done this, if you know about this ASCII encoding, all it does is saying, okay, I'm going to assign every letter a unique number, okay? So it's like, okay, there's, 26 letters in the alphabet, and like I'm going to assign a number 1 to 26, okay? And then like I send everything in bits, so it's like, okay, this everyday English sentence becomes this many bits, okay? All right, so that's like, a very standard way to encode things. Now Huffman encoding is a much smarter way to encode things that saves a lot of like space, okay? Saves a lot of bits. Okay, so now what is Huffman encoding motivated by? Let's say in the English language, certain letters are more common, right? So let's say, I just made this up. Someone made this up, just like this is a distribution of letters that you'd expect to see, okay? So maybe like 8% of all the letters are A, and maybe like 14% are E's, and so on, okay? Then it's kind of like wasteful to encode like this, because essentially everybody is kind of using the same, every letter is using the same number of bits. That means like, well, things that are like really frequent, like E, are using the same number of bits as things that are super infrequent, like Z. Then it seems kind of imbalanced, okay? So how do I formulate this? Well, it's like, okay, imagine like the distribution of, there's only 6 letters, and like, 45% of the time I'm using A, 9% of the time I'm using E, and so on, right? And because there's 6 things, I'm using, 3 bits. And there's like, well, it's very wasteful because some of the encodings are never even used, right? Like 110 is never used. And like, well, because A is used so much, right? I'm sending A over and over again. Like, I'm writing A over and over again. Well, if I just could write A with like 2 bits, then that would actually save me on the long run, right? Because I'm 45% of the time I'm using an A, okay? So how do I model this mathematically? Well, let me just skip this. Okay. So my goal is to come up with a tree, okay? Okay. The leaves of the tree will be the individual letters, okay? And like in this 45, this means 45% of the time I have an A, okay? And now I go from the root to the leaf, and that's how I encode every letter, okay? So A is going to be encoded as 0, 0. B will be 0, 1. F would be like 1, 0, 1, 0. B would be like 1, 0, 1, and so on, okay? This type of coding is called a prefix-free, meaning actually like if I take 2 letters, like it's not going to be the case that one's encoding is a prefix of the other, okay? Because they're all on a path, root to leaf path, right? So it's not going to be like someone is at an intermediate node, right? That would be a prefix. That would be bad for coding purposes, because if somehow like A was 0, 0, and B was like 0, then you wouldn't know whether it's B, B, or A, okay? That's why you need this prefix-free property, so that's like uniquely decodable, right? So just the fact that it's a tree makes it unique, okay? Like meaning, if I see a bunch of zeros and ones, I know exactly what the letters are, because nothing is sharing like prefix with anything else, okay? All right. And now the cost of a tree is sort of like, if I sort of sample a letter from this distribution that I expect to see, right? 45 time I'm doing A and so on. What is the expected number of bits that I use, okay? So what is this calculation? It's saying, well, for A, right, I'm using 2 bits. So 45% of the time I'm using 2 bits. 16% of the time I'm using 2 bits. Some percent of the time I'm using 3 bits. So that's so on average, right, in some average sense, I'm using 2.39 bits, right? This encoding cost me 2.39 bits on average, okay? And right, so this is only with respect to like this distribution of letters that I give you, okay? So the problem is, right, right, so just to give you some intuition, right, what you want is you want things that are super frequent to be higher up in the tree, okay? Because then you're encoding it with fewer and fewer bits because you're using it more and more. And you want things that are like very infrequent to be super deep in the tree because you're only going to call them very, this is how I'm defining the problem, right? I care about this expected value, okay? All right. So just to kind of write this mathematically, right, I'm going to define the cost of a tree to be the following, okay? I need all the letters to be at the leaves. And I say, okay, every letter has a probability of being picked, okay? That's given to you, all right? That's known, okay? That you know that. But the thing I care about is minimizing this cost, okay? What is this cost? It's sort of like the probability of selecting the letter times the bits used for that letter, okay? So it's how deep is it in the tree. So to go back to this example, right, it's like 45% of the time I'm going to have an A, and then I pay 2, okay? So that's why it's 45% of the time I pay 2. So this is the expected value, okay? Right, so this is much better, just to contrast it with the previous thing, right? This is much better than getting every letter 3 bits, okay? Then like all the time I'm using 3 bits on average, right? Because everything uses 3 bits, on average it also is 3 bits. But this way you save something, right? Like on average I'm doing less than 3. And the thing I'm exploiting is like I'm really going to make the letters that are super frequently called have really short codes. That's how I save it. And actually some things might get like super long codes, but that's okay. That's the trade-off that I'm paying for, okay? Right, so this is the problem that I care about, okay? So this is the definition of the problem. I have some n letters, let's say, or n symbols. I want to encode them as bits. I want to do this in this tree way, okay, so that everything is uniquely decodable. Nothing is a prefix of the other. That's a property that the tree has. And the thing I care about minimizing is this, the probability of this sort of weighted average, okay, which is kind of roughly says, if on average I pick a letter according to the distribution I care about, how many bits am I using to encode it? All right? And this can often be much smaller than like the naive thing, which is, right, if I have like 16 things, I use 4 bits. That's a naive thing. But here, I'm using like the distribution to kind of do slightly better, okay? So of course, if the distribution is uniform, I can't do better than this naive thing. But if it turns out that like 100% of the time I only use 1 letter, I never use any of the letters, then I just use that. I just use 1 bit, right? No matter how many letters I have. So then I save a lot, okay? So this is a problem I care about, okay? And this has a nice name. It's called Huffman encoding, named after this guy, Huffman, back in the day. And it's a greedy algorithm, right? So this is a very complicated objective I care about, right? It's like I'm minimizing across all trees this weird objective function where I care about the average number of bits. And this has a greedy algorithm, okay? You can build this tree greedily, okay? So I'll show you the greedy algorithm. I won't prove why it works. There's something I posted on the canvas that proves it. Proof is a little bit hairy, actually. But yeah. But really, the idea is like you want to push less frequent letters towards the bottom. You want them to use as many bits as possible, because what that means is towards the top, you have very frequently used letters, okay? So this is how the algorithm works, okay? So let's say I have I have 6 letters, and this is sort of the distribution, okay? 45% of the time I have A, 13% of the time I have the B, and so on, okay? So this is how I build a tree, okay? I pick the 2 least frequently used letters, and I add this node, okay? I connect them. Now I'm going to build a tree, okay? Okay. Then I pick the next 2 least frequently used things. Then the next 2 least frequently used things, okay? So why did I pick these 2? Well, it's like kind of when I pick these 2, I kind of merge them, and I imagine that's like a new letter in the alphabet. So then, like, 14 and 16 were the least, right? Because the rest was 25 and 45, okay? So just to see one more step, right? The first step, I pick these 2. Then the next, I pick these 2. Then I pick these 2. And then I pick these 2. And then I pick these 2. Okay? So this is, if I give you this distribution, this is the optimal way to encode them, right? Look, so A only gets 1 bit, 0, right? So even that's like, 45% of the time, I'm only using 1 bit. Whereas, F gets 3 bits, or even 4 bits, right? It's very long. It's like 1, 1, 1, 1 is the F. Okay? And like I said, this has the property that, right, no code is a prefix of another code, okay? Like, it's not that, like, there's no 1, 1, 1, right? If there was a 1, 1, 1 and a 1, 1, 1, 1, like, you'd be confused, right? Which one is it? But here, nothing is a prefix of the other, okay? Right. So does the algorithm make sense? I'm greedily selecting 2 things to merge into a node, okay? And it's actually pretty fun. Like, you can kind of look up the, distribution of letters in the English, whatever, dictionary, and figure out what is the average number of bits you need for this optimal encoding. It is not going to be like log base 2 of 26 plus 1. That's like the naive way. It's going to be slightly smaller. It's actually going to be quite a bit smaller, okay? And like you can say, okay, the expected cost is 2.24, right? How did I get that, right? A, right, 45% of the time I'm paying 1. 41% of the time I'm paying 3, right? So how do I get this 41? It's like, okay, I'm not sure how this math works, but okay, it's 2.24, right? It's like this weighted average. Okay. All right, so in code, it just looks like this. It's basically what I said, right? I pick 2 of the least frequently, 2 of the existing, like, frequently used letters. I like merge them into like a super node, okay? And then I pretend that's my new letter, okay? And then I like repeat the process, okay? So that's all this is saying. This is called Huffman coding. Yeah. And then let's sketch a proof, okay? So it's going to be same like swapping idea, okay? But like the actual proof is more complicated, so I'm not going to show it to you. If you're really interested, right, it's on Canvas. So let's say that, right, let's just show one step, okay? Let's say that like X and Y were the 2 least frequently used characters, but somehow they didn't end up together, right? Ideally, it would be X and Y connected, right? That's how the Huffman algorithm works. Why was it that there was some other letter here? And the claim is, well, then I can swap X and A. Why, right? Well, the reason is A is more frequent than X, right? Well, then if I swap X and A, well, then A actually has a shorter encoding, so that if I do the expected value calculation, I win. Okay, so that's all this is saying. If the 2 least frequently used things are not together, I can swap the thing that is with, and then still get an optimal tree. Okay, so I can do the swap. And then, like, how do I show that this continues to work? So that works for the first step. Well, the basic idea is like, if I merge 2 things into a node, then I can actually just pretend it's another new letter, right, called, T, right? Some new letter that doesn't exist, that is actually like has a 14% probability. And then I reduce to the same case, okay? So that's how the official proof works. It's just like you keep imagining new letters that combine other letters. But essentially, the cool thing is, right, this is a very complicated objective, but a greedy algorithm still works, okay? and it's called Huffman coding. It's actually pretty fun to play around with. Okay, so if you have time, you should do it. Yeah, that's it for the class. Thanks.